There is yet a third type which we call rational inequality. This is similar with the makeup of a rational number or even rational function, but the procedure of solving a rational inequality is similar with quadratic inequalities. Learn more about it here in Mathematics of Engineering. We start by having a quick review of rational functions. Just like rational numbers, taking the format of the ratio of two integers where the denominator should be a non-zero integer, rational functions are also the ratio of two polynomials whereby the denominator shouldn't be equal to 0. The solution of rational inequalities is still similar with the other types, although there would be a minor distinction in the equating of terms. Let's explain the procedure better with an example. Say we have the ratio of 3x plus 1 with x plus 4 is greater than or equal to 1. We have to place a 0 onto the right side of the inequality, thus we should subtract both sides by negative 1 to have the quantity of 3x plus 1 upon x plus 4, and everything is less 1, and this is greater than or equal to 0. From here on, we can generalize the denominator for all terms, so we subtract x plus 4 in the numerator, after which we can simplify the terms in the numerator into 2x minus 3. This is the simplified rational inequality that we would test for ranges of x. We continue by equating both the numerator and denominator to the other end of the inequality. So we get 2x less 3 is greater than or equal to 0, and the other is x plus 4 is greater than or equal to 0. Focusing on the inequality from the numerator, we add 3 on both sides to have 2x is greater than or equal to 3. Then we can move on isolating x by dividing both sides again by 2. Then we get x is greater than or equal to 3 halves. Next, we process the inequality from the denominator. X plus 4 is greater than or equal to 0. Subtract 4 on both sides to arrive at x is greater than or equal to negative 4. We look further into this root, as it is in the denominator, regardless of what inequality symbol we have. If we take x as negative 4, we get 0 in the denominator. We cannot have 0 in the denominator as it makes the whole inequality indeterminate. So we use negative 4 as a marker with an open interval because negative 4 cannot be a root. With the two roots identified, we can draw the number line with an open interval on negative 4 and a closed interval on 3 halves. So having 2 marks for the inequality, we get 3 sets of tests to work on. So from the range of negative infinity and negative 4, we can use x equal to negative 5. Substitute negative 5 in the inequality, and we end with 13 is greater than or equal to 0, which is a true statement. We work on the second range from a lower limit of negative 4 and an upper limit of 3 halves. We assume this time x as 0 for this range. And plugging the assumption in the inequality, we have negative 3/4 is greater than or equal to 0. This is a false inequality statement. The third range is between 3 halves and positive infinity. We use 2 for x. Place this in the inequality and have 1/6 is greater than or equal to 0. This is a true statement. After identifying valid ranges, we can conclude that x can be from negative 4 way down to negative infinity, and also with 3 halves up to positive infinity. So in interval notation, we write the ranges as an open parenthesis with negative infinity coupled with negative 4 and enclosed in another parenthesis. Then we have a union with the bracket of 3 halves paired with positive infinity and again in a parenthesis. Example 2 is with x minus 8 all over x is less than or equal to 3 less x. Move everything on the left side by subtracting 3 and adding x on both sides, so we have the ratio of x minus 8 with x less 3 plus x is less than or equal to 0. Distribute the denominator on all terms, so we have x less 8 minus 3x plus x squared all upon x is less than or equal to 0. Simplify the numerator to x squared less 2x less 8, and this can be factored, giving us the simplified rational inequality as the quantity x minus 4 with another quantity x plus 2 all upon x is less than or equal to 0. Having two terms in the numerator, we have x minus 4 is less than or equal to 0 and x plus 2 is less than or equal to 0. The other term equated to 0 is the one from the denominator, and that is x is less than or equal to 0. Again, regardless of the inequality symbol, we cannot take 0 for x as it will zero out the whole denominator, making the inequality indeterminate. With x minus 4 is less than or equal to 0, we find the root by adding 4 on the left and right to have x is less than or equal to 4. The other inequality of x plus 2 is less than or equal to 0 can be simplified by subtracting 2 on both sides, which gives x is less than or equal to negative 2. Graphically, we mark negative 2 and positive 4 with closed intervals to signify lesser than or equal to from the numerator inequalities. The other mark under 0 is from the denominator, thus we use an open interval. Now we can test the ranges for true inequality statements. Starting with a range between negative infinity and negative 2, we assume an x value of negative 3 in the inequality, and this gives 11/3 is less than or equal to 6, and this is true. In the next range, we use negative 1. Have this in the inequality to get 9 is less than or equal to 4, which is false. The third range is between 0 and 4. We try x is equal to 1. Plug this in the inequality and we get negative 7 is less than or equal to 2. This is a true statement. We can assume x as positive 5 for the last range between positive 4 and positive infinity. By placing this in the inequality, we have negative 3/5 is less than or equal to negative 2, and this is a false statement. By drawing out the true statements, we can place an arrow from negative 2 all the way to negative infinity, and the other is between 0 and positive 4. In interval notation, we have the union of the first pair of negative infinity and negative 2 with the pair of 0 and positive 4. The next example has the square of x less 16 all over the square of x minus 1, and this is less than 0. The numerator has difference of two squares, so we can expand it as x plus 4 and x less 4. The denominator has a repeated term of x minus 1. We can now equate terms in the inequality. So from the numerator, we have x plus 4 is less than 0, and x minus 4 is less than 0. From the denominator, we have x minus 1 is less than 0. By subtracting 4 on both ends in the first inequality, we get x is less than negative 4. We also add 4 on both sides of the second inequality to have x is less than 4. The last inequality will be simplified by adding ones, and we have x is less than 1. But then again, regardless of the inequality sign, the root taken from the denominator shouldn't be 0, so it will always be an open interval. Graphically, we can summarize the markers as open intervals at -4, at +1, and +4. Having 3 markers, we generate 4 ranges. The first one of which is from -infinity to -4. Taking x as -5, we get the inequality 1/4 is less than 0, which isn't true. The second range limits the x value between -4 and +1. Say we take 0. Plug this in the inequality to have -16 is less than 0, a true statement. From the third range, we can take +2 as it lies between 1 and 4. Use +2 in the inequality to have -12 is less than 0. This is again a true inequality statement. The last range is between +4 and +infinity, so we take +5. Using this as x in the inequality, we have 9/16 is less than 0, which is false. So we can connect the appropriate markers according to the true ranges, and those are between -4 and +1, and also +1 and +4. Take note that 1 is an open interval, which means +1 is not included in the range of roots, so the interval notation will be separated as a pair of -4 and +1 in union with +1 and +4.